In the ternary diagram, we have three binary eutectics that come together to form the eutectic trough of a ternary eutectic. The eutectic points in each of the binary systems project into the ternary systems as curves. Any composition on one of these curves will crystallize the two phases on either side of the curve. In the 2D diagram below, we have our boundary curves as well as our isotherm temp lines. Our ternary eutectic is this point E. Let's consider our stainless steel to be a chromium-rich stainless steel of composition X. To determine the crystallization path that our composition X will follow, we will draw a straight line through our chromium vertex in our composition X to the boundary curve. Once we reach the boundary curve, we will follow it as we continue to cool until we reach our eutectic. So our crystallization path will look like this. And then we will follow the boundary curve until we reach the eutectic. Let's say we begin to cool and find a temperature of interest that we'd like to determine the percentage of solid and percentage of liquid. Let's call this Y. If we want to determine our percentage of solid and liquid present, we will take our distance from Y to X and Y to our chromium vertex, let's call this Z, as well as our distance from X to Z. Our percentage of solid will be our distance X to Y divided by our total distance YZ, and our percentage of liquid will be based on the length of X to Z divided by our total distance Y to Z. Our distance from X to Y is going to be 2 centimeters. And our total distance will be 6.8 centimeters. Therefore, our percentage of solid is going to be 29.4%. Our distance X to Z is going to be 4.8. Again, divide this by our total length from Y to Z of 6.8 is going to yield 70.6% liquid. Now as we continue to cool and reach the boundary curve, let's call this location A. As we cool from A along the boundary curve, we will reach point B. If we are interested in our percentage of solid and our percentage of liquid at point B, we must construct a line from point B through our original composition and intersect the opposite side of the triangle. Now I'm going to call the point where we intersect the opposite side of the triangle point C. To determine our percentage of solid, we would take our distance from point B on our boundary curve to our original composition X and divide it by our total distance from B to C. Similarly, to determine our percentage of liquid, we would take our distance from C to X and divide it by our distance B to C. Now that we know what our percentage of solid and liquid are at point B, let's determine our percentage of iron in the solid and our percent of chromium in the solid. To determine our percentage of iron in the solid, we will take our distance from point C to our chromium vertex and divide it by our total length from iron to chromium. And to determine the amount of chromium present, we will take our distance from C to the iron vertex divided by our total distance from iron to chromium. It should make sense that we have a higher percentage of chromium in our solid at this point because our original composition is chromium rich. So to determine these percentages, our points of interest are our iron vertex, point C, and the chromium vertex. Our distance from C to chromium is 3.1 centimeters. And our total distance is 16.8 centimeters. This is going to give us 18.5% iron in the solid. And for our percentage of chromium, our distance from the iron vertex to point C is 13.7 centimeters. Again, dividing by our total length from iron to chromium of 16.8 is going to give us 81.5% chromium in our solid.